Hello and welcome to a new video in a course on calculus. In the previous video, we discussed the definition of sequences, and we talked about the notions of convergence and divergence. So in this video, I plan to go over some of the most important tricks in calculating limits of sequences, and we'll be going over proofs of some of the most important limits you'd see in calculus. So before we do that, let us just do a little bit of recap of what we did last time. So I remind you, we made a definition. So we defined sequences with the notation an as a list of number that can be infinite or finite, where repetition is allowed and order matters. And then we said that some sequences tend to have some behavior, right? Like they have some trend, they tend to something, in the sense that if you consider the sequence an, which is equals to 1 over n, for example, and you write a few terms of these, like you write a 1 over 1, the first term, 1 over 2, the second term, like this is for n equals 1, this is for n equals 2, and so on. 1 over 3, right? And so on. You see that eventually what you're doing is that you're having 1 over a huge number. Like as you go, as you increase the n, right? As you increase the index, you're gonna have 1 over a huge number. And 1 over a huge number, this is close to 0, right? So it seems that as we increase n, as n tends to infinity, it seems that this sequence is having some trend, it's tending to something. And this is what we call the limit of a sequence. So, just to make a recap here, here's the definition that we made. Just a little bit of recap here. So the definition is that a sequence an is said to converge to a limit L if for every small number epsilon you can find there exists. So this means for every, and this means there exists a number n that you can think of as a huge number, such that if you look at an and you subtract L, the distance is going to be less than epsilon, which means that this is for n bigger than n, which means that if you choose an index big enough, the sequence is going to be close to L in an epsilon distance from L, right? So this is the definition of convergence, and a sequence where its limit doesn't exist was said to be divergent, right? So we mentioned that we only need this definition. We only need to use this definition to prove two basic limits. In fact, there are others that are important, but for now, these are the things that we need. We proved two basic limits, which is, the first one was that the limit of 1 over n is equals to 0, right? The limit of the sequence 1 over n, an equals to 1 over n, this goes to 0, right? Just as we justified, like, because we have 1 over a huge number. But to prove this mathematically, we did this proof, so you can refer to the previous video to see this. And the next thing that we did was that we proved this limit. We proved that if you have a constant and you take, you have a sequence that is a constant, meaning, let's say you have an is just the constant 2, then you have 2, 2, 2, this is the sequence, right? It's just a list of 2's. Then where is this sequence going? Well, intuitively it's going to 2 as n tends to infinity. So and you can actually prove this mathematically as such, and you can refer to the previous video to see the proof of this. Now, as I mentioned, the definition including epsilon is a little bit beyond this course, so we're gonna only need it for these examples, and from now on we're gonna be introducing tricks to compute limits, right? So so let me just before we start doing some tricks of limits, let me just give you some properties of limits that are important when that are important to use when you want to calculate limits. So I'm gonna present a few of these, right? So here are the properties of limits that you would need. The limit of a sequence an plus a sequence bn as n tends to infinity is equal to the limit as n tends to infinity of the sequence an plus the limit of the sequence bn as n tends to infinity if the limits of these two sequences exist. So let me give you an example here, right? Let me give you an example. So the limit as n tends to infinity of the sequence 1 over n plus k plus 2, for example, right? So I just proved to you that 1 over n as a sequence, it converges to 0, right? Its limit is 0. And I just also proved to you that the limit of a constant sequence is the constant itself, right? This is what we talked about in the previous video. So for you to be able to say that this is 0 plus 2, you're using this property. You're using that you can distribute the limit. You can take the limit of the first thing plus the limit of the second thing. And you can use the above two properties that we proved, or two theorems, and you can see that this is 0 plus 2, right? Which is 2. So in other words, the limits they respect the arithmetic operations. Like they respect the plus, the minus, and the times. They also respect the division under a certain condition that we're gonna talk about. So so as I mentioned, it also respects subtraction. Like you can, if you have a subtraction of two sequences, the limit of the difference is gonna be the difference of the limits, right? So you can just separate the limits as such. Meaning, for example, you can have a similar thing to here, right? So the other important property is that it respects multiplication, in the sense that if you have a limit of a sequence an times bn, provided all of these limits exist, the limit of this thing is equal to the limit of an times the limit of bn. Right? So let us take an example here. What is the limit of 2 over n, right, as n tends to infinity? Right? So so intuitively you would think, well, let's write a few. So this is the sequence an in this case. So let us write a few terms of this sequence. So it's 2 over 1 for n equals 1, and then 2 over 2 for n equals 2, and then 2 over 3, 2 over 4, and so on. And what you see is that as n increases, as n goes to infinity, what we're having is we're having 2 over a huge number, right? As n increases, we're going to have 2 over a huge number, which is namely n, and this is intuitively close to 0. So there's some notion of so there is some kind of trend happening, or the sequence is tending to 0. So this is intuitively, but why is it true by what we proved? Well, the reason it's true is because this is the limit of 2, right, times 1 over n. So you don't need to do these steps usually, but for you to understand where things are coming from, so later on you can just use the fact that this will be 0 automatically, right? But because we're proving it right now, right? So it's the limit of a sequence that is a constant sequence 2, and this is multiplied by another sequence. But where a second limit actually respects multiplication, which means that this is the limit of the first sequence times the limit of the second sequence. In this case, it's 1 over n. And we know that the limit of a constant sequence is just the constant itself. So the limit of this limit is just 2 times the limit of this this sequence is 0. We proved it. So 2 times 0, this is just 0, right? So the last property I want to tell you about is that if you have the limit of an over bn is equal to the limit of an over the limit of bn, this is provided, let me just say, if bn and its limit, let me just say, if the limit of bn is not 0, right? So if the limit of bn is not 0 and you have this, you can also separate the limits in the sense that the limit is like actually respects division. So let us take a quick example over here. Here's an example. Take the limit of 1 over n, all of this divide by 2, for example, right? Or all of this divide by 2. What is this? Well, this is the limit of the thing above divided by the limit of the thing below, and this is just the limit of the numerator is 0 and the limit of the denominator is 2, and this is just 0, right? So so these are the properties of limits you would need to know when calculating limits of harder or more complicated sequences, right? So these are the properties, and how do you remember these? You just remember that limit respects the usual arithmetic operations. For example, it also there's one that I missed here, which is that it respects the multiplication by a constant, but this follows actually from this one, right? Because you can take the first sequence to be the constant sequence, and it follows immediately. So let me just state this. So it also respects multiplication. So if you have the limit of a constant times a sequence, this is the same as the constant times the limit of that sequence, right? So it respects the usual arithmetic operations that you know of. Now that we've discussed the properties of limits, it's time to start doing some tricks. And these tricks that these are like kind of theorems that you will be using when computing limits of more complicated sequences. So let us start by the first trick or theorem. So so here's the idea of this theorem. The idea of this theorem is that you want to use the information you know about sequences that bound your sequence to get the limit of your sequence. So what do I mean by that? So before we talk about the theorem, let us just look at this example, right? Let's look at this example. If you look at this example, if I ask you what's the limit of an as n tends to infinity, if I ask you this question, you initially have no idea what this limit is, right? However, you notice something immediately. You notice or you recall that the sign of a number is between 1 and -1, right? If you're taking a sign of a real number, you have this inequality, right? So so this immediately gives you this inequality, right? Because you can bound this by 1 and you can bound it below by -1. Okay. So so now you bounded the sequence between two things, but let's see. This thing, we know it goes to 0, like we proved that the limit of 1 over n is 0, right? And we also proved that the limit respects the arithmetic operations. So the limit of -1 over n is negative the limit of 1 over n. So that goes to -0, which is 0, right? So so the limit of this thing is between two things, is between 0 and 0, so it must be 0. So in other words, what we did here is that since the limit of 1 over n is equal to the limit of -1 over n is equal to 0, it follows that the limit of sine n over n as n goes to infinity is equal to 0, right? So intuitively speaking, if a sequence is bounded between two things and these things go to a number, then the inner thing, the thing in between these two, should go to that same number. And let me state the theorem now. Let me state the theorem in a more generality. If you have a sequence Bn, and this sequence Bn is bounded between two sequences, An and Cn, and I should stress here, important note, this should happen for every n. What do I mean by that? I mean, for example, if you take if you take the sequence 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so on, right? If you take this first sequence, and you take the other sequence, let's say 1 over 2, 1 over 3, 1 over 4, and then you have 1 over 3, right? If you notice here, since you're dividing by bigger numbers below, then the thing above is going to be bigger. So the first term is bigger, the second term is bigger, the third term is bigger. However, if you go to the if you go to the fourth element of this sequence, you see that this is bigger than that. So the inequality doesn't hold for every n. So because it fails for index 4, right? I'm stressing here that the sequence, these sequences, or this property, this inequality should hold for every n, right? So if that happens, and the limit of an is equal, this is very important, they should match. Like the limit of this and the limit of this, they should match. If they are equal to some limit L, then the limit of Bn exists and it's equal to L. And you can intuitively see this, because if you have An is between Bn and Cn, right? Then this is going to L and this is going to L, thus this must go to L, right? So this can be proven using the epsilon definition, but you can take this and use it as a tool from now on. So before we go to the next tool or theorem, let me give you another example. Let's say we take the sequence -1 to the n over n, let's say, right? So if you write a few terms of this sequence, so it's gonna be for n equals 1, this is gonna be -1 to the 1 over 1, so this is -1, and then for n equals 2, it's gonna be -1 to the 2, which is -1 squared, which is +1 over 2, and then -1 over 3, 1 over 4, and so on. So if you look at this sequence, what's happening is that it's alternating, right? It's sometimes plus and sometimes minus. It's sometimes negative. So it's not clear immediately what this sequence is going to, right? It's kind of it's alternating between positive and negative numbers. So should it go to a positive number? Should it go to a negative number? Should it go to 0? So how would you know? Well, here's an immediate way of seeing this. So -1 to the n over n, right? Let's try to use sandwich theorem. Let's try to sandwich this sequence between two sequences, right? So let's keep the n as is. What's the biggest this can get? Well, the biggest this can get is 1. And what's the lowest, or what's the smallest it can get? Well, the smallest it can get -1, because for different values of n, this is plus or minus 1. So this is also bounded between, so this sequence is also bounded between 1 over n and -1 over n. But we know that this goes to 0 and that this goes to the same thing, to 0. Then the thing in between these, the sequence in between these, should go to 0 by squeeze theorem or sandwich theorem. Alright? Alright, so on to the next tool. So the next tool we need here, so the next tool we're going to introduce is what's so-called the continuous function theorem for sequences. So what is that and how is this helpful? Okay, so let me just give you a quick idea of why this is helpful, right? So let's take an example to see why this theorem is important. So let us recall that the function f of x equal to exponential of x, like it's e to the power x. This function is continuous, right? So this function is continuous. And so if I ask you the question now, what's the limit of e to the 1 over n, right? E to the 1 over n as n tends to infinity. So this is a sequence, and I'm asking you what's the limit of this sequence. So since the function is continuous, what is this theorem telling us? This theorem is telling us if you have a continuous function f, and you take a limit of it, you take the limit of f of n, f of 1 over n in this case as n tends to infinity, which is the limit of the sequence that you want, right? If you take this, you can pass the limit inside the input of the function. So you can pass it to the input as such, if it is continuous. So what this means is that this is just f of what? This limit, we computed it to be 0, which means that this is the same as e, because f of x is what? E to the x. So if this is x, then this is e to the 0, and this is anything to the 0 is 1, so this is 1, right? So so in other words, if you have a continuous function, you can pass the limit to the input of that function. And we're gonna see more examples of these, but let me state the theorem in a generality now. So if the limit of a sequence an is L, it exists and it's equal to L, and f is a continuous function, then if you take the limit of f of an, if you take the limit of f of that sequence, then the limit will be the same as f of the limit of the inside, right? So you can pass the limit inside of f, and this, if this is L, then this is f of L, right? We're gonna see an immediate example, an application of this, and this theorem is very important, right? We're gonna see an example to convey how important it is. So let's take an example here. Let's look at this. Limit here. So if you look at this sequence, if you look at the sequence a n equals to n to the 1 over n, and if you attempt to take the limit of this, what is that? Well, this is infinity 1 over infinity. So the limit of this is this thing. I mean, what the heck is that thing, right? So if you look at this, it's not clear, right? It's not clear what the limit is. So how can you know what the limit is? So you start trying the tools tool by tool. You say, okay, so let's try if I can do it by sandwich theorem. So what can I bound this by, right? It's just not clear, right? It's not clear what to bound this by, right? When we were working, for example, with minus 1 to the n over n, like this can be bounded. You have a bound on this, so you can make sense of what bound would be, what the bound would be. But in this case, like it's not clear, right? It's not clear what the bound, or like the upper bound and the lower bound of this would be. So here's the power of the continuous function theorem. So I remind you, one important function. One important function that you might have encountered in a freshman class is what's so-called a logarithm. So it's the ln function. And what's one property of the ln function? One property is that if you take the len of a to the power b, then this is the same as b log of a, right? So since this power is annoying here, right? Since this power is annoying, we want to like apply the logarithm to it, because this would simplify the way of getting the limit, right? So this is an important limit for you to understand. So please stick around here. So here's the idea. The first, let's try an example. Let's do it for an example, and then you'll get it for a general x. So what is the limit of 1 plus 1 over n to the power n? Well, the first thing to try is to see if you get nice things when you just evaluate at infinity. So what is this? This is equal to 1. Let me just put these between quote and quote. This is equal to 1 plus 1 over infinity, which is 0 to the power infinity. And this is equal to 1 to the infinity. 1 to the infinity is undefined. So you run into trouble. So you can't just do evaluation. So we need another way to prove what this thing is. And interesting enough, this is going to be the exponential function. So it's going to be e to the power the number x that you're using. In this case, it's going to be e to the power 1. But why is that the case? I mean, is there an easy way to see this? So what is annoying here? If you notice here, what's annoying here is that we're having an n, because the n is resulting to a power of infinity. So we're having this annoying n over here. And how do we usually get rid of exponent? We usually take what? We usually take the logarithm, right? So let's call this sequence an. Let's call this sequence an equals to 1 plus 1 over n to the power n. And let's look at the logarithm of it. If we take the log of an, or the len of an, this is going to be, the n is going to be down here, and then we have the logarithm of 1 plus 1 over n, right? And we recall the nice property that the logarithm and the exponential are inverse functions. Then this is an equals to e to the log of an. And this is the same as e to the power n log of 1 plus 1 over n, right? And now we need a little bit of trick, because we might be able to prove this using L'Hopital's rule, which we're gonna talk about in a few. But here's another way to see this. Man, you're doing a lot of mistakes. You should do L'Hopital's rule. Yeah, you should do L'Hopital's rule. Yeah. This is another trick for computing limits. So we're going to study this, do some examples on this, and then go back to use this and the continuous function theorem to compute more complicated limits. So let us see what L'Hopital's rule is. So let me state the theorem. Let me state what the rule is, and then we're going to do an example. So here's what the theorem is saying. So if you have two functions, f and g, that are nice, let's say these are nice functions, and you don't need to know much about this because most of the functions that you'll encounter in this course are nice. Few examples might not be, but most of these will be nice. So there is some way to define what nice is, but it's beyond this course. So let us just say that we have some nice functions, and you want to compute the limit of f of x over g of x. For example, let's say you want to compute the limit of log of n over n as n tends to infinity, right? So in this case, more generally, you have two functions and you want to compute the limit of that. What the rule says is that to compute the limit, for example, here the first function f of x is log of x, and this is g of x equals to x, right? Evaluated at n. So if you want to compute the limit of such a ratio, right? And when you plug the value of x, when you plug, for example, the x equals c or the x equals infinity, in this case, if you plug the value of x, and this has the form 0 over 0 over infinity. So we're gonna do a quick example right now, but stick with me. If you evaluate x at the point that you're trying to take a limit to, and it gives the form 0 over 0 or infinity over infinity, then what the theorem is saying is that the limit of this ratio is the same as the limit of the derivative of the numerator over the derivative of the denominator. So why is this theorem important, and what is it really saying, right? So let's take a quick example. Let's take an immediate example to make things clear, right? So let's do this example. For example, say we have the sequence log of n over n, right? And we want to compute the limit of a n as n tends to infinity. So as n tends to infinity, the first thing to try when computing limits is to see what happens if you quote-unquote plug infinity there, right? So what happens is that you're going to have log of infinity, which is infinity over, instead of n we have infinity, so it kind of have the form quote-unquote infinity over infinity. And you go back to the theorem, if it has the form infinity over infinity or 0 over 0, then you can use L'Hopital's rule. And what does L'Hopital's rule say? It says that if you're taking a limit of log of x over x as x tends to infinity, in this case, this will be, what will this be? This is gonna be the derivative of the numerator over the derivative of the numerator, right? And why is this important? Well, the derivative of x is just gonna be 1, right? So you're gonna be getting rid of this ugly denominator, right? So this is gonna be the limit of the derivative of x is gonna go here, which is 1, and the derivative of log is gonna go here. I remind you, what's the derivative of log? The derivative of log is 1 over x, right? So this is gonna be the limit of 1 over x as x tends to infinity. And we just, this is just what? This is just the limit of x as x goes to infinity of 1 over x. We're just dividing by 1 here, not a big deal. So what is this limit? Well, we computed this limit before. We computed what the limit of 1 over n as n tends to infinity. And it's not so hard to see that this is 0, right? So the limit of this function is 0, but it wasn't immediately clear when plugging the infinity, like quote unquote plugging the infinity. It wasn't immediately clear. We had to use something. We had to use that this limit is the same as the derivative over the derivative, right? And one important thing here that I should warn you about, the theorem here is missing one condition, which is that the derivative of the function should not be 0, right? The derivative should not be 0 because you don't want to divide by 0. So this is what we have, right? So for example, you can't apply this theorem when g is a constant, right? Because the derivative will be 0 and then things won't be so nice. So like we just use a very powerful tool to compute a limit that is not very clear what it is, right? It's not very clear what the limit of log of n over n is, right? And here's a cleaner solution for you. So you want the limit of this, you take the derivative. It's the same as the limit of the derivative evaluated at n over the limit of the derivative evaluated at n, and it's the same as this thing, right? So keep this limit in mind, keep this answer in mind, that the limit of log of n over n is what is 0, right? Keep this in mind, we're gonna need it in a few. Let us take another example, because these are important examples. So let us take another example here. What's the limit as x goes to 0 of sine of x over x, right? Again, the first thing to try when trying to evaluate a limit is to quote-unquote plug the value in, because it might be indeterminate form. So you first of all attempt to plug things in. So this is sine of 0 over 0. And what is sine of 0? Sine of 0 is just 0 over 0, quote-unquote. So this has the form of 0 over 0, and we go back to the theorem. What's the theorem saying? If you want a limit of a ratio of two functions, and it has the form 0 over 0 or infinity over infinity, you can take the derivative up and down, right? So why are we thinking of L'Hopital's rule here? Well, the reason we're thinking of L'Hopital's rule is because we have a ratio of two functions and we're interested in the limit, right? So what would the answer be then, right? What would the answer of this limit be? So you apply L'Hopital's rule because you have the form 0 over 0, and when you take the derivative up and down, so let's see, so this is sine of x over x, this is equal to what? The limit as x goes to 0, derivative below is 1, right? And the derivative of the sine is what? Is cosine, right? And now you try to plug things, to plug 0 again, and you get cosine of 0 over 1. What's cosine of 0? It's 1. So it's 1 over 1, which is 1. So we just computed that the limit as x goes to 0 of sine x over x is what? Is 1. Right, which wasn't clear immediately. I stress here, it wasn't clear immediately. It wasn't clear initially that this thing is 1, right? If you haven't used L'Hopital's rule, that's not clear why it is actually 1, right? So here's a cleaner solution. You want the limit of this, you take the derivative, because it has the form 0 over 0. You take the derivative and you take the derivative below, and you get this thing, right? So I stress here another thing, which is it should have this form. If it doesn't have this form, you can't just say the limit of the ratio is the limit of the derivative of the numerator over the derivative of the or of the denominator, right? So let's do another example using L'Hopital's rule, right? So what's the limit of ln over n over n to the k as n tends to infinity? So I remind you, we proved in a previous slide that the limit of the log of n over n as n tends to infinity is 0. So intuitively, because we're dividing by a bigger power of n, we're dividing by a bigger number, intuitively you should think that this is 0, right? Of course, for k a positive number. So you should think that this is 0, but why is it really 0? Like, is it immediately obvious? Because remember, we can't just do things by intuition here. We have to prove things. Why is it 0? Well, just recall, like we're interested in a limit of a ratio of functions, right? We're interested in the limit as x goes to infinity of log of x over x to the k, right? We're interested in this limit, and since we're interested in this limit, we might think that L'Hopital's rule is a good tool to use here. So the first thing to try is to plug things in, so quote unquote plug infinity. So log of infinity is infinity over infinity to the k, which is infinity, and it has the form infinity over infinity, right? So it has the form infinity over infinity. So by L'Hopital's rule, you have that the limit of log of x over x to the k as x goes to infinity, it's the same as the derivative over the derivative, the limit of the derivative. What's the derivative of log? 1 over x. What's the derivative of x to the k? It's k x to the k minus 1. And what is that? You rewrite things. You divide this by 1 and you multiply things out, and you get this is the same as 1 over k x to the k, right? Because you multiply this and this. And well, what is this? This is just 1 over infinity, which is 0, right? So your guess was actually right, but it wasn't immediate. You see here we have an indefinite form. And to prove this, we had to use L'Hopital's rule. And here's a cleaner solution for you. So you start with this. It's the same as the limit of the derivative evaluated at n over the limit of the derivative evaluated at n. And this is the same as this thing. And when you take the limit, you get a 0. So we're going to do one more important example of calculation of limits that's going to use both L'Hopital's rule and the continuous function theorem. So let us go back to the continuous function theorem and do this very important, like it's one of the very important limits that you might encounter. So you want to prove that the limit of 1 plus x over n to the n, as n tends to infinity, is exponential to the x. Like, where is the exponential coming from? Like, it's not at all obvious where the e is coming from, right? So let us see how to prove this. So here's one way to do it. So let's do it for a simpler case where x is 1, though it's literally the same, but just to simplify notations. So let us prove that the limit of 1 plus 1 over n to the n is equal to e to the power 1, right? So why is this the case? So let's see why. So the first thing to try again is to try to use the rules that you know. For example, you try to use squeeze theorem, and it's not clear, right? It's not clear what would be an upper bound and a lower bound of this. What would lower bound this and what would upper bound this? It's not clear. And you try to use, you think of using L'Hopital, but you don't have a ratio of two functions here. So what is it that we have to use? You remember that one way of getting rid of an ugly exponent is by taking logarithm. So if we call this sequence an, we can write an, I remind you of this trick, this is a very important trick, you can write it as exponential of logarithm of an. And this is what? Because these are inverse functions, right? And this is what? This is e to the, so what's the log of this? The n is going to be down here, and this is going to be the log of 1 plus 1 over n. Now, you look at this, and again, like, it's also not clear what the limit of this is, right? So if you take a limit of an as n tends to infinity, it's the limit of this thing. It's the limit of this thing. And what is this? So the first thing to try again is to plug things in, to plug things, like to plug n by its value and see what you get. But before we do that, let us rewrite this in a nicer form. So let us rewrite it as the log of 1 plus 1 over n over 1 over n, right? So we can bring this n to the denominator by making it 1 over n, right? As n tends to infinity. So now try plugging things in. So if we try plugging things in, this is what? Like 1 over n here is going to be 0, and the 1 over n here is going to be 0. So this is e to the log of 1 plus 0, which is log of 1 over 0, which is e to the 0 over 0, right? So in the exponent of e, right, we have a form 0 over 0 because we computed the limit of this. And why are we allowing ourselves to pass the limit to the exponent? Well, it's because the exponential function is continuous. And when the function is continuous, I remind you, you're allowed to pass the limit in, right? So what we want to do now is we want to compute what the limit of the log of 1 plus 1 over n over 1 over n as n tends to infinity. Because if we can find what this thing is, we can just plug that as a power of the exponential function, and this would be our answer. So what is the limit of this thing? Well, I remind you, when we try plugging things in, we get 0 over 0, right? So this should call your attention to the use of L'Hopital's rule. So you apply L'Hopital's rule, and what is this? This is the the limit as n tends to infinity of you take the derivative of log of 1 plus 1 over x, and you take the derivative of 1 over x below. And what is that? So what is that? This is minus 1 over x squared, the derivative of 1 over x, evaluated at n, so it's going to be 1 over n squared. It's going to be minus 1 over n squared. We're derivating the function, not this function of n. So we're derivating the function log of 1 plus 1 over x, and this is minus 1 over n squared over 1 plus 1 over n. And like this thing and this thing will cancel out, and what you'll be left with is the limit of 1 over 1 plus 1 over n, and this is what? This is 1 over, so you know what the limit of this, right? So you know the limit of this is 0, so this is 1 plus 0, which is 1, right? So as we claimed before, sorry, this is a little bit of a mess, but let us just recap things here. So we started with an, we write it as the exponential of log of an, and we rewritten this as exponential of n log of 1 plus 1 over n, and then we rewritten this as exponential of log of 1 plus 1 over n over 1 over n. This is what we have. And then we said that the limit of the an as n tends to infinity, since the exponential function is continuous, we can pass the limit to the exponent. This is the limit of this, right? 1 over n. And we just computed what this limit is. We just computed it over here, right? We just computed what the limit is, and it is 1, right? So this is going to be e to the 1 as we claimed, right? As we claimed over here. It's e to the 1. So, let me just clean things up here. And I'm going to leave this proof to you to stare at, like the cleaner proof, the typed proof. I'm going to leave it to you, for you to stare at. It uses another method other than L'Hopital's rule, which we're gonna prove later, which uses Taylor's expansion, and we're gonna talk about this later. So you can stare at this proof if you'd like. Otherwise, you can mimic the proof I did for x equals 1. So here we did the proof for x equals 1, right? So here we did the proof for x equals 1. So you can mimic this proof that I did to you, and then you can do the same for this thing in general. And you can stare at this proof. This is another proof that I thought that it would be cool to leave for you. So you can stare at this proof, and you can just decide if it looks good to you or not. But we're gonna come back to this later.